In our previous video, we started with the observed frequencies for the combination of our two categorical variables, and then calculated the expected frequencies that we would expect to see if in fact those two variables were independent. We'll now use the observed and expected frequencies to calculate our chi-square statistic. Now, to calculate the chi-square statistic, you take the frequency that you observed for a specific combination of the two variables, subtract the frequency that you expected to see for that combination, then square that difference, right, and divide by the frequency that you expected to see for that combination. You then repeat this for each combination of the two categorical variables, adding up the result each time. Now, you may notice that it's the same formula as the chi-square for the goodness of fit test, and that's right, it is the same formula. The difference is that here we're looking at the combination of two categorical variables. So it's the same formula, just applied in a different way. So let's start doing the actual calculations now. As we just said, to calculate our chi-square, we need to plug in the observed and expected frequency for every combination of our two variables. So let's pull those up. Here are our observed frequencies, and here are our expected frequencies if nationality and sport are independent. Now, keep this handy because we're going to be referencing these values over and over and over again as we calculate our chi-square. And remember, we have to calculate the observed frequency minus the expected frequency squared divided by the expected frequency for each of these cells. So let's create a blank matrix just containing the generic equation for each of these cells. All right? And we'll start with this first cell in the first row, those in the US whose favorite sport is baseball. We observed 18 people, but expected 19.2 if sports and nationality are independent. So let's calculate the value for that cell, that combination. It's just 18 minus 19.2, that difference squared, divided by 19.2, that solves to 0.075, and let's put that in the cell up here then, all right? Now, let's move on to the next one. Those in the US whose favorite sport is basketball. We observed 30 people, and we expected 30 people if sports and nationality are independent. So look what happens when we calculate the value for that cell. It's just 30 minus 30, which is 0, right? We square that 0, it's still 0, and we divide by 30, and it's still 0. So let's put that up in its cell. Now, notice what happened. For this combination, US and basketball, we observed exactly the same number that we expected to see if the two variables are independent. So what does that combination contribute to our chi-square value? Contributes absolutely nothing, which makes sense, doesn't it? The closer the observed frequency is to what's expected, the smaller the contribution of that specific combination to our chi-square value. All right, let's keep going and look at those in the US whose favorite sport is football. We observed 62 people and expected 53.4 if sports and nationality were independent. So the value for that cell is 62 minus 53.4, or 8.6 squared, then divided by 53.4. That works out to 1.385. So let's put that up in its cell, all right? And we'll keep moving on to the final box for the USA group, those in the US whose favorite sport is soccer. We observed 10 people and we expected 17.4 if sports and nationality are independent. So the value for that cell is 10 minus 17.4, or negative 7.4 squared and divided by 17.4. That works out to 3.147. And we'll put that up in the value for its cell. Now, notice something else here. The difference between the observed and expected frequency for USA soccer fans is negative 7.4, which is smaller in absolute terms than the difference between the observed and expected frequency for USA football fans, which is 8.6, all right? But notice that soccer makes a larger contribution to our chi-square value. It adds 3.147 than does football, which only contributed 1.385 to that chi-square value, even though the football difference is a little bit bigger. Interesting, isn't it? Now, why might that happen? Well, you can think of it this way. Look at the relative size of the two groups. The expected number of people picking football, 53.4, is much larger than the expected number for soccer, which was only 17.4. So a given difference for soccer is a bigger deal than that same difference for football. It may help to take this to an extreme. A difference of, say, 8 people when you only expected 10 is relatively a lot more than a difference of 8 people if you were expecting 10,000. The same difference in absolute numbers of people is a bigger deal with a smaller group. Right? Kind of makes sense, doesn't it? Now, that's our chi-square calculations for the USA cells. Why don't you now do the same calculations for Canada on your own? Pause the video and start up again when you're done, all right? Are these the values that you got? If they're close, it could be due to rounding. Now, if you didn't get these values, go back and double check your calculations. I'd suggest actually redoing them while watching me go through the calculations for the USA row, all right? Now, before moving on, there's one of the values I want to point out. Note the 0 for the Canadians who prefer basketball. Were you a little surprised that you got 0 just like we did for basketball with the US sample? Right? But if you think about it more, it kind of makes sense. Remember, we didn't change the total number of people in the basketball column. So if out of that group of people who pick basketball, if the number from the US was exactly what we would have expected, then the number from Canada would also be exactly what we would expect, right? Now, that works in this specific case because we only have 2 boxes in that column. If we had 3 or more, 1 could be the exact number that we expected and end up being 0. And the other two could be a little off. One might be higher, one might be lower, and so they wouldn't be 0. All right? And remember, before moving on, that because these are all based on squared values, none of the values can be negative. If something's negative, you know you've made a math error somewhere, so go back and figure it out. All right? Now with that, let's move on and calculate our chi-square statistic. Remember that for each cell, the formula is the observed frequency for that cell minus the expected frequency for that cell. That difference squared then divided by the expected frequency for that cell. That's what we've just calculated for each of these cells. We then just add up all of those values across all of the cells. That's what that big summation sign's for, right? So for our data, that works out to be 0.075 plus 0 plus 1.385 plus 3.147 plus 0.113 plus 0 again plus 2.078 plus 4.721. That's a lot. We add up all of those and we get 11.519 as our chi-square value. Excellent. All right. Now, remember as well that chi-square is our test statistic. It's a number we calculate from our data that's sensitive to whether the null or alternative hypothesis is true. In the case of the chi-square statistic, the larger the chi-square value, the less likely it is that the null hypothesis is true, that the two variables are independent, right? The less likely it's that the two variables are independent. Okay? Now, to determine whether our chi-square of 11.519 is large enough to reject the null, we need to compare it to the chi-square probability distribution, right? And as we've seen, though, with the chi-square goodness of fit test, the shape of that chi-square distribution varies based on the degrees of freedom, just like we saw with the T and the F distributions. For the chi-square test of independence, the degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1, which for this example is just 2 minus 1 times 4 minus 1, or 3 degrees of freedom. All right? Now, if we combine this with our chi-square value, we could formally write out our results just like we did with the chi-square goodness of fit test as chi-square followed by parentheses with 3, the degrees of freedom, comma, n equals 200, our sample size, and the parentheses, equals 11.519. That's how we write it out, right? Now, remember, include the sample size because the chi-square degrees of freedom don't give us any indication of how large the actual sample size was, okay? So next, let's visualize what this chi-square value looks like, okay? Now, here's a chi-square distribution with 3 degrees of freedom. This reflects the probability of getting different chi-square values with 3 degrees of freedom if the null is true. In this case, if the two variables are independent. So the first step we might do is determine our critical chi-square value, that value that we need to reject the null hypothesis. Now, why don't you pause the video and using the chi-square magic calculator or some other table or calculator, see if you can determine what the critical chi-square value is. Remember, our alpha was 0.05. All right? Restart the video once you've done that and are ready to move on. Did you get 7.815? Remember, if alpha is 0.05, the critical chi-square is the value beyond which only 5% of the distribution lies. That's the shaded red area here, right? Only 5% of the time would we randomly get a chi-square greater than 7.815 if the null is true. It's our line in the sand, remember. If our chi-square is greater than 7.85, we feel the results are just too rare if the null is true. So we conclude the null probably isn't true and we reject the null hypothesis. Now, what did we see with our data? With our data, we obtained a chi-square of 11.519. So right there, we know we're going to reject the null because our chi-square is more extreme than that critical chi-square. But just how extreme is it? What's our p-value? Remember that the p-value is the likelihood that we would have obtained a result this extreme, a chi-square of 11.519, or more if the null is true. That's equal to the area in our chi-square distribution that's more extreme than our observed chi-square of 11.519. So if we look that up, we find that the area above a chi-square of 11.519 with 3 degrees of freedom is equal to 0.009. Our p-value is 0.009, which is less than our alpha of 0.05. So again, it's consistent with the conclusion that we would reject the null hypothesis. Excellent. All right, so let's summarize what we've done. Our research question was whether a person's favorite sport was dependent on their nationality, living in the US or Canada, to be precise. We set our alpha at 0.05, meaning we were comfortable committing a type 1 error, rejecting the null even when it's in fact true, only 5% of the time. Our null hypothesis is that sport and nationality are independent. The probability of favoring a different sport was unrelated to whether one was from the US or Canada. Our alternative hypothesis is that sport and nationality are not independent. The probability of favoring a given sport is different based on whether one is from the US or Canada. And our sample size was 200, right, with 120 people from the US and 80 from Canada. So what do we find? Well, based on our sample of 200, we obtained a chi-square with 3 degrees of freedom equal to 11.519, which has a p-value of 0.009. Because p is less than our alpha, our statistical conclusion is that we'll reject the null hypothesis. In English, our substantive conclusion is that preference for a favorite sport does appear to be dependent upon nationality, at least when comparing people from the US and Canada. All right? So that's the chi-square test for independence from start to finish. Remember, it's a test for when we have 2 categorical variables. That's the big difference between it and a Z or T test. All right? Now, hope you found this helpful, and I'll see you in the next video. Bye-bye.